Alright, so as we continue looking at trig, and we're laying the foundation for all the other cool stuff we really want to do later, the next step here is to start thinking about what the graph of a sine curve would look like and start identifying some different features. And we're going to do that just a little bit today, and then we're going to focus the majority of our time today on identities. Okay? Now, to start out looking at the graph, one thing we have to understand is that sine and cosine, and in fact all of our trig functions, are what are known as periodic functions. Okay? That means that when I'm looking at my angles on my unit circle, and I go around all the way, if I keep going, guess what's going to happen to the value of sine?
Get back to 0.
It's going to get back to 0, and then if I keep going 30 degrees past, let's say to 390,
Is it the same as when it was 30?
it's going to be the same as when it was 30, okay? Because this circle keeps doing the same thing over and over and over again. And what you just described now is the whole concept behind what a periodic function is. The values are going to repeat every period, okay? That's why it's called a periodic function. If we were to graph the sine curve, and we said, okay, hey, when the angle is 0, what does sine equal? 0, okay? See if we can do this here. When the angle is 0, the sine is 0. When the angle is pi over 2, which is the same as 90, what is sine? Where'd it go?
1. I have it.
Where did it go?
Sine is 1.
Hang
It's
on.
really weird because I have it here.
My
Yeah,
graph,
I have it too.
my graph disappeared.
Bro, what
I
do you
don't know.
Maybe.
Well, we'll redraw it. It's okay.
Unimportant to watch.
I don't know how that happened. I just opened the file.
Damn, Brett.
Okay. So here, if I'm looking at it and my x is the angle I'm working with, and y is the value of the sine at a given angle, then like you said, when the angle is 0, I'm at 0. And when the angle is at pi over 2, we're where?
90?
It's 90 degrees, but what's the value of sine?
1.
1. Okay. What about when I get to pi?
0.
We're back to 0. How about 3 pi over 2,
-1.
which is the same as 270? We're at -1. And then
0.
I get back to 0 when?
At
It's
360.
360.
At 360 or 2 pi, okay? So, guess what? This is what our sine curve looks like. Okay? That's what our sine curve looks like. And guess what it'll look like if we kept going?
It's the same thing.
Identically the same, okay?
DNA.
That's why this is called a periodic function, because every 2 pi, or 360 degrees, this same little segment is going to repeat. This is one period. And in the case of sine and cosine, it equals 2 pi.
But is the amplitude pi over 2?
No, we'll get to amplitude. That's a little different, okay?
Amplitude.
Now, this period is actually related to something you might be familiar with if you're into music or sound or whatever. Sound waves, we talk about frequency, okay? Like when an orchestra is tuning, they usually tune to the A440. You know, the oboe will play it, and then you have your first chair violinist will play it, and then everyone tunes off of that. It's the A440, okay? That means that to play an A, the string has to vibrate 440 times per second. In other words, we have a sine curve that is doing 440 periods in a second. Okay? That's what determines the pitch. If we slow it down to like half of that, towards 220, we still have an A, but it's an octave lower. If we double it to 880, it's still an A, but it's an octave higher. Okay? That's why mathematically you can design, different pitches based on their frequencies. Okay? That's all related to period. Okay? Now, what makes music louder or softer is the amplitude. And that is how high or how low it goes. Okay? Now, you'll notice here the x-axis is kind of a center line here. We can move the sine curve up or down or whatever. You're always got this center line. And in this case, in the normal sine curve, it's at the x-axis. Well, the distance that we go from that center line up or from the center line down is going to be our amplitude. Okay? And to find our amplitude, we're going to take half the distance between that max and the min point. Or I shouldn't say point, the max and the min value of the function. Okay? So amplitude is the max minus the min all over 2. Okay? Well, what is the max on a sine curve?
1.
1. What is the min on a sine curve?
Negative 1.
Negative 1. 1 minus a negative 1 is 2. So that means our amplitude is 2 over 2. It's 1. Okay? And again, that's because if you look at this center line, we go up 1, there's our amplitude, and we can go down 1. There's our amplitude. Okay? Yes?
Does it start at that 0 or does it kind of go negative?
Can we have negative angles?
Like with the curve, like can it go like down the other way and then come up like
Yeah.
the negative direction?
I'm trying to answer, can we have negative angles? Yes. So yes, this actually does, if we kept going to the left into the negative angles, you would see the same thing. The domain for sine actually is all real numbers. Okay? So good question though. Now, let's do the same thing here with cosine, and that'll actually take us to the first of the identities that we want to look at today. Okay? So let's run through this. Thinking about our unit circle, what would the cosine of 0 degrees be? It's, wait,
1.
1.
it's the x-coordinate, right?
1.
So 1,
Yeah.
okay, it's 1. At pi over 2, what does cosine equal?
0.
0. At pi, what does cosine equal? Negative 1. At 3 pi over 2, it's
0.
0.
and at 2 pi, it's
1.
1. So check this out. This looks an awful lot like the sine curve. In fact, it is identical to the sine curve, except it has been shifted, translated.
1.
Okay? And it's been shifted
Pi over 2.
pi over 2. Okay? That right there is where we get the first of our identities that we're going to look at today. Okay? If you take a sine of an angle, and then you take the cosine of pi over 2 minus that angle, you will actually get the same thing. These are what are called cofunction identities. Okay? Let's look a little closer at this first quadrant. Okay? This first quadrant, the sine of 30 degrees, we go through our points here. 30 is the point root 3 over 2, 1/2. And the point here at 60 degrees, or pi over 3, is 1/2 root 3 over 2, right? So notice here the sine of 30 equals what?
1/2.
1/2. The cosine of 60 equals 1/2. Okay? So, sine of 60, or I'm sorry, the sine of 30 equals the cosine of 60. Okay? If we look at the sine of 60 equals root 3 over 2. Cosine of 30 equals root 3 over 2. There we have it. Okay? What's this point right here?
Root 2 over 2.
Root 2 over 2,
Root 2 over 2.
root 2 over 2. And check it out. The sine and the cosine of 45
So you really only have to find 2 points
are the same.
to find the rest of it.
Yeah, theoretically, yeah. Okay? Now, what do you notice about 30 and 60 and 45 and 45?
They're complementary.
They're complementary, okay? They're complementary. That means that they, what does that mean?
They add up to 90.
They add up to 90, okay? That's where we get this idea that the sine of an angle will equal the cosine of 90 minus the angle. That's the definition of what a complementary angles are. The cool thing for us is that that doesn't just apply in the first quadrant. It applies no matter what theta is. Okay? If we deal with this in radians, it would be the sine of theta equals the cosine of pi over 2 minus theta. One thing I will mention about this is that it is not uncommon at all to see people write this as theta minus 90 instead of 90 minus theta. Okay, so just be aware of that. Okay, but this is how we will learn it. Now, this doesn't only apply for sine and cosine. This is where the pairings of our other trig functions are the simplest to remember. Sine is paired with cosine, so secant is going to be paired with cosecant. Tangent is paired with cotangent. Okay? This is why these are called the co-function identities. Each of these functions is paired with its co-function. Alright, so these are the easy ones to remember.
Why do we write pi over 2 minus theta?
To show that, I mean, it's not sine of theta equals the cosine of the same angle. The angle has to be complementary to it. Okay? So the angle that we're taking the cosine of is the complement of the angle that we're taking the sine of.
How can we use that?
I mean, it just varies depending on the problem, depending on what we're working with. Okay. We'll actually see on the practice that I'll give you, we'll see some cases where, you know, if I knew what, let's say I know what the sine of a 15-degree angle is, I automatically know what the cosine of a 75-degree angle is, because 15 is 90 minus, or 75, okay? So, we can use it for those types of things. Alright, so that's one set of identities. The next that I want to focus on today here is our Pythagorean identities. Now, someone take a wild guess and tell me what we're going to use to develop these identities.
A squared plus
Yeah, the Pythagorean theorem. A squared plus b squared equals c squared. Except, we're going to use on our unit circle the fact that the hypotenuse will always be 1, right?
Yep.
So if I were to rewrite the Pythagorean theorem here in terms of what I've got, I could say that y squared plus x squared is going to always equal 1, right? So on the unit circle, if you take the coordinates and you do the y coordinate squared plus the x coordinate squared, you'll always get 1 squared. Okay? Now, let's think though, because we know what y is in relation to our angle. What is y in relation to the angle?
The sine.
It's the sine of the angle. So guess what we could plug in? We could plug in
Sine. plus
sine
cosine.
squared of the angle.
Sine squared plus cosine squared, the angle is equal to 1.
Yep. Remember, x is our cosine. And by the way, notice I'm writing the square after the sine and after the cosine, not after the angle, because we're not squaring the angle. We're taking the sine and then we're squaring that. So we put the square after the sine, after the cosine, then we write the angle. Okay?
So for sine and cosine, you're not plugging in like 1/2 and root 3 over 2, you're plugging in the angle measure?
You could, but you could replace the entire sine of theta with a 1/2 or
Yeah.
root 3 over 2. If I were plugging in something into this, I would plug in the actual angle, because that's what this is taking. Okay? So guess what? This is actually our first Pythagorean identity. Sine squared plus cosine squared equals 1. And the cool thing is that one's pretty easy to remember, and the other two are very easily derived from this. Okay? In fact, a lot of times, just to double check myself before I say it out loud, I'll rederive the other two in my head. Okay? So, let's see how we're going to derive the second one. Okay? To derive the second one, I'm gonna get a 1 right here where the cosine squared is. So I'm going to divide by cosine squared. And if I do it there, of course, algebraically, I have to be fair to everything. So I've got to do it there, and I've got to do it here as well. Okay? Now, I already said this is going to give us a 1.
Oh, it's gonna be tangent. Oh, because that's tangent.
What's tangent?
That's tangent. Sine squared over cosine.
Sine over cosine is tangent, so sine squared over cosine squared would be
Tangent squared.
tangent squared. There we go. So tangent squared plus 1 will equal, what would 1 over cosine squared equal?
Oh.
Secant
Squared.
squared. Yeah, 1 over cosine is secant. So this is going to be secant. Secant
That doesn't work again.
C.
squared. Okay? And guess what? That's our second Pythagorean identity.
Tan squared theta plus 1 equals cosecant.
What?
If you divide by sine, it would still be 1 plus, oh no, it wouldn't be tan.
Okay, but you're on the right track here. Philip, did you have a question before we go?
Yeah, could you just do that again? Or you just turn it into
Here, we had looked at from our unit circle that sine over cosine is tangent.
Yeah.
So sine squared over cosine squared will be tangent squared.
So, but then wouldn't that mean that tangent squared would be equal to 1 over cosine? Because you still have 1 over cosine squared.
Yes. So 1 over cosine is secant, so 1 over cosine squared is secant squared. So this is our Pythagorean identity. The tangent squared plus 1 will always equal the secant squared. Okay. Now, what Carly was saying is correct. We're going to take this, and we're actually going to do something similar here, but in this case, we're going to divide by the cosine. Okay? So let's divide by the cosine.
By the sine.
Sine.
Or sine, yeah, sorry, we already divided by cosine.
I was like,
So we're dividing by the sine squared, there, and here,
that was to be cotangent.
okay? And you're right, notice here sine squared over sine squared is 1. Since tangent is sine over cosine, then if we flip that cosine over sine, we get cotangent. So this is cotangent squared theta.
Equals cosecant.
Plus 1 equals
Squared.
Cosecant
Cosecant
squared.
squared, yeah.
Yeah, there we go. 1 over sine is cosecant. So 1 over sine squared is cosecant squared. Okay? And that right there is our third Pythagorean identity. Okay? So again, if you can remember sine squared plus cosine squared equals 1, then you can pretty easily get the other two. Okay? That's why I show you how they're developed, okay? Took me a long time to get to the point where I actually had them memorized, so I would just constantly re-derive them in my head. Now, just a little preview of where we're headed with this is the fact that if I had an equation like this that had a sine squared and a cosine in it, I couldn't solve that. But we will be solving equations like this. In order to do that, though, I would have to recognize, hey, if sine squared plus cosine squared equals 1, I can subtract cosine squared from both sides. And I know sine squared is a 1 minus cosine squared. Okay? So now I have an equation that only has cosines, and I'm able to solve it. Okay? Now, let me just show you this table. This is straight from your book. Okay, this does not show the cofunction identities, but those you do need to know. These, however, are ones that you're going to be using thousands of times by the end of this year. Okay? These are known as the fundamental trig identities. The reciprocal identities, the quotient identities, and the Pythagorean identities. They're not the only ones we're going to use, but these are really the most significant ones, the ones you're going to use the most, and you need to get working right now on memorizing those. Okay? So you really, really know them well. Okay? Now I gave you some practice on these. Use your identities. Okay? For the last section, use your unit circle. Okay?
Identity crisis.
All right. We'll see you guys. Have a great day.
Bye, Mr.